So, mostly I will talk about what is morphism of pre-varieties. See, in the affine case, when x and y affine, so general definition is what that general definition is that if you have two pre-variety means what, you have some x over x. X is a topological space. X is a topological space. Recall, this is definition. Recall. So you call it a pre-variety. X is a topological space, and over X is a sheaf of k-valued functions. On X, such that X you can cover it by some finite open cover. It has a finite open cover, I equal to 1 to n. And these UIs are affine. UIs are affine variety. UI affine variety. And this now if you have a sheaf on a bigger topological space, you can restrict basically the inverse image of the sheaf. So OX restricted to UI is nothing but O of UI. But OUI is a sheaf of regular functions on the affine variety. So this is the condition. This is the definition of pre-variety, right? And then and suppose Y is another pre-variety. So Y OY, another pre-variety. Then a morphism abstractly defined as XOX to YOY, F hash, where F is a continuous map. And F hash is takes OY to F lower star of OX, right? This was the definition of pre-variety, right? Now, what does it mean? This means this so first condition is okay, is not that abstract. But second condition means that for every u, so this checking this condition is for all u in Y, F star or F hash, or how do you say? Yeah, F hash. Let me write this. OY of u. This goes to OX of F inverse u. That is, if I take a function here, say alpha, then this goes to alpha composition F, right? So this alpha goes to alpha composition F. This is for all u and for all alpha. So now this is for every, see, first of all, so now can you simplify this definition? So like in the affine case, when X and Y are affine, you just had to check that this giving a F, and yeah, so this F which is say X is X and X is a affine, then this is equivalent of giving this map F hash at X or Y. right? The global functions, which is nothing but Ox, Oy of y, which is Ay, right? So let's write y then. F hash of y, which is a map from Ay to Ax. Only you have to check with this function, this open set y. You don't have to check for the other open sets. Yeah. So this was the, and there is a one-to-one correspondence between, and giving a map like this will induce a map from y, x to y, right, and vice versa. So it was very concrete. But as forget pre-variety, if x is projective variety, say x is projective, when and if y is affine, you know that there are no non-constant maps, right? Because the regular. But if y is projective, say both are projective, then how do you explain a map from x to? So given two concrete projective varieties, say subvariety of some Pn and subvariety. So this is sub of Pn, and this is sub of Pm. Point is that how do you say that there is a map from x to y? Because there is no global function, global map. So the mostly what you do, you define some hook or crook. You define a map, set theoretic map, and then you prove that it is a morphism. So you need to guess. So even for when x equal to p1, so that means this is called rational curve. So given a variety y, whether there is a map from p1 to y, so that means whether there is a rational map, rational curve or not. Of course, P1 to a point you can always define. Everything goes to a point. That's always a map. But you don't want such trivial map. You want a which should be infinite or should have some non-constant image. So it's a $1,000 question. It's not easy. So maps between two projective varieties, even simple, forget pre-variety, two projective varieties, is not easy to say that I give you two variety, concrete variety. I say, can you construct a map? You have to think about it. It's not, there is no, because there is no global, it's not, there is no global maps. You can, there is no commutative algebra analog like in affine case. So between two rings, you can always think whether it's one can, there is some kernel, one is quotient of something, and then you think of, so there is no such thing in the projective variety thing. So things are hard. Given a map, you can do many things, but this kind of questions, that whether you can construct a map, is not easy. So now the point is that can you give some condition so that you say that it's a, so one way is constructing a map. You give on smaller pieces, you give maps and then you try to glue. But then again, that's a very cumbersome work. Another thing is that you define a set theoretic map from x to y and then say that when it is a morphism. Give a criteria that give a map from x to y, set theoretic map that you can always produce using polynomials, but one has to check that's a morphism. Being a morphism is a little bit tricky, right? It has to take each regular function to regular function. So to check the second condition, so this is the next proposition. Mostly checkings are usual checking, but one has to do such checking to say there is a morphism. So x, y are, So let's write XOX, YOY are pre-varieties. And AF is a map from X to Y, map, not a morphism. So it's a set map. I want to say when it is a morphism. I want to put a criteria. So let Y union of, so Y is a pre-variety. So this is Y I equal to 1 to n, be a collection of open affine subsets and X you can write it as UI, I equal to say 1 to m, finite cover, be an open covering, need not be affine cover. It's a topological space, so open covering makes sense. So now such that, so you have two open cover, but the Y has a affine open cover and X is any open cover, such that the map to that you have this set map F of UI is in Vi. Okay, this let's write same notation, same index I equal to 1 to n. Both are by same number of open subsets. And F hash is the map from OY of Vi to OX of UI. Right. If F of UI is Vi, right. So if this is the case, so that means if this happens, then F is a morphism. So it is the, what does it says say that it is not very bad in the sense that you just have to see whether there is such open cover such that this happens. You don't have to check for every open set. See, in general X to Y, the pre-variety, you have to check for every open set. But what is saying that you do it for one affine cover. So first of all, I did not choose UI to be a affine, but as you know that I can choose UI to be, without loss of generality, I can choose UI to be affine. Because after all, AX is a pre-variety, so it is covered by affine open subsets. So if I choose some open subset UI, then I can take, so I can take some affine cover of X, say UI tilde, and take UI tilde intersection UI. That will be in UI tilde. So that will be affine. That is also in UI. So for every UI, I can choose a U, which is in the which is a affine open subset. So UI prime. So without loss of generality, we can assume that these UIs are also affine. So without loss of generality, so one can assume. So this is remark without generality, one can assume UIs are also affine. So now what does it say? That means that to check a map of pre-variety, you just need to check for affine cover, that X and Y are covered by two affine open subsets with same number. same number of affine open subsets. So the f of ui is inside vi, and this f, the map, it sends the oi of vi to oi of ui. Okay. So now proof is so you have this. So you define f of I to be f restricted to ui. Okay, and now this sends ui to vi. So now fi will induce some map of at the ring level, a of vi or a of vi, which is nothing but oi of vi, right? Ring of regular functions on vi. A of vi to a of ui, which is ring of regular functions on ui. The sheaf of, right? Now this is a map of algebra, k algebras. So this will induce a map gi from ui to vi. Right? So what does it say? That means that this is a map of affine varieties. So that means gi is nothing but this fi restricted to or f restricted to ui, which is nothing but fi phi. Right? Map of algebra that gives a gives a map of topology, the affine varieties. And so this fi is nothing. So locally, this is a map of affine varieties, because this is a sheaf of because of this condition that this is the oi of vi goes to ox of ui. Right. So locally, it's a map of affine varieties. Now the point is that can you construct so now so you have a map f, which is just a map from x to y, and these fi's are continuous map, and f restricted to fi is f restricted to ui is fi. So that will say that f is continuous. Right? If you have a map of x to y, if a map of topological space, and if you restrict to each open subsets ui, if they are continuous, and because it's a map, so they matches on the intersection. So then the function f is also continuous. So this implies f is continuous. So now only thing to check is that this that f takes this it takes the regular functions to regular, or the sheaf to the sheaf. Yes. Because this fi is inducing the map fi hash. See, fi hash is, so giving a map fi hash is equivalent of giving a map fi. See, fi I did not know what is this fi, but fi is giving a map, but giving a map of affine variety is same as giving that sheaf level map. So now you come down to the sheaf level map, and that gives a natural map because of the correspondence. So now fi has to be gi, because if the fi induces fi hash. This yes, this is, yes, this f hash is coming from f, right? So this is, I am using just the fact that k finitely generated k algebras, the category of finitely generated k algebra and category of affine varieties, these are equivalent categories.
Sir, are they isomorphic?
Which are isomorphic?
Finitely generated k algebra and
these two categories, they are equivalent.
Yeah, equivalent, but are they isomorphic? Isomorphic as categories?
Yes, that is what equivalence of category means. That if you have a category C and D, then you
They are
say
naturally isomorphic if identity.
yes. It means that there is a map G. So the G composition A. There is a natural isomorphism with the identity functor.
I was asking if they are equal.
This will not be equal. There is isomorphism involved. Equality is there not a yeah. It won't be equal. Everywhere there is some isomorphism. Okay, so now only thing to check that this F, which is a continuous map. So now the map, all this. So we know that F is a continuous map. So now only thing we have to check this F hash takes regular functions on Y to regular functions on F inverse of U. So if I so to check now, so now the F hash takes regular functions on V, say V is open in Y, to regular functions are on F inverse of V. Right. So how do you check that? So what you do, so you know on UI and V, so F inverse V intersection UI. So there, so if you take some say okay. So let's write this. So let's let G belongs to OY of V. Okay. So what I need to show that G composition of A belongs to OX of F inverse V for all V sub of open subset of Y. This is the thing I need to check, right? But what I am saying that now you consider F inverse, but this is true for each Vi. So now F inverse of V intersection UI. So F inverse of V equal to union of F inverse V intersection UI. Now you consider this. There is a this is a sheaf map, right? This is a OX is a OY, OX is a sheaf. So consider G restricted to this F inverse of V intersection UI. Or let's write G composition F, right? G composition F is an element of OX of F inverse V. Now what you do, you restrict it to F inverse V intersection UI, right? But now because UI to Vi, this is a map of affine varieties. So this belongs to OX of UI. But see but F inverse, but GOF, but now you use the sheaf property that this is a GOF. So on each affine open, they are regular. So that will say that it will extend to a regular form, because on an open subset, it's a regular if and only for each affine pieces it is regular. So that will say that G composition F is regular. right? That's how you define for any variety. You define a regular function is that for every if you have a cover, if for every, because it's a cover, so for every point you have a restriction is a regular function. So and that they glue. So it is because it's coming from the function g of f. So that will say that this is a regular. So these kind of arguments will come again and again. That whenever you don't have anything, you are not working with affine varieties, so you go to a cover and then you locally you study, and then the argument you go to the you do this at the global level. So now, so the point, the point is that you can reduce the case that you don't have to check for all open subsets, you just have to check for some certain open covering. You construct some open covering, and in the projective space, most you know one such open covering exists. Yeah, the standard affine open subsets, right? In the when you are doing projective, suppose X is a projective variety Pn, then you know that such a or X is sub of Pn, then you know that X you can write it as union of ui, where I equal to 0 to n, and these ui's, each ui's are affine. So what you do, you take xi to be x intersection ui. So x is union, then x is union of xi. Each xi's are affine. And then for each affine piece you do. So now you want to construct x to y. Suppose you want to construct a map. X is a projective variety, y is some p of m, right? That's what I started with, that you given two projective variety, how do you construct a map? So then similarly for y you can write it as y union of yj or yi, where yj is y intersection vj, where vj's are the standard affine open subsets, right? Because see, Pm you can write it as union of Vj, j equal to 0 to m, and then Yj you can write it as Vj intersection y. So what you do now? So how do you construct a map from x to y? You construct a map from x, some abstract map first you define f, set theoretic map, and then you show that when you restrict this map to xi, they are nice. They take regular functions to regular functions, because these are affine, xi and yj. So this is how it is done in practice. That how do you construct a projective map between two projective varieties? So you break your projective variety into affine pieces, you construct a map which is a set theoretic map, and then you show that that map has this property. It takes the regular functions on each affine open subsets of X to this affine. So this is how map of this is one way of constructing maps. You see, okay. See, you have to go through all these things because there are no global maps. See, maps between projective varieties, and projective varieties are when you study algebraic geometry, you study projective varieties. I mean, otherwise there is no, most theorems are for projective varieties. You can prove. So maps between projective varieties, they are very important to understand how. So they are not easy. See, to get a, first of all, there are many difficulties. Difficulty is that how do you construct such f first of all? Even two abstract projective variety, how, I mean, just given by some homogeneous polynomial, right? X is given by some set of zero set of some homogeneous polynomial, y is some zero set of some homogeneous polynomial. How do you construct? That means you have to construct at a, so x will be some v of I, right? I is some homogeneous polynomial, y is some v of j, and this I is some polynomial in say kx naught up to xn. and j is in some k y naught y m. So what you have to construct a map from k the map from kx naught to this such that it takes the ideal to the ideal j, so that it's a 0 set will go to the 0 set, right? That's how you prove. So you construct such map, and then there you set theoretic map, then you try to see that whether it satisfies the morphism properties. So there are a lot of work. I mean, it's not easy. Okay. So these are questions always. I mean, these are some open questions are there that given a projective variety, whether there is a rational curve, or how can you count such rational? Can you classify rational curves? So there are some varieties called Fano varieties. So they have a lot of rational curves, and many varieties which are called general varieties, they don't have any rational curves. And whether it has a rational curve or not, rational curve means whether you have a map from P1 to that variety. This is the simplest case. When x is P1, so I am considering x to y. So simplest case is when x equal to P1. When this is a curve and this is a curve of simplest kind, which is this is a simplest curve, projective curve. And this y is any projective variety. Whether there is a map from P1 to y. Given a projective variety, are there any map from P1 to y? Non-constant maps. Right? We want to know that. So there are varieties which will say that you have to you need to introduce some more techniques to say that such thing. So questions are very easy to formulate, but answers to find an answer you have to you need to use a lot of cohomology theory or many. I mean, it was so this was in 90s. This was quite 90s, 80s. This was so for when y is 3 dimension, whether it has a rational curve and having rational. So this was a topic of interest for many people, because Mori proved using this some conjecture which is called Hartshorne conjecture, using rational curves inside the projective varieties. So this was this is a topic of interest to many. I mean, this is a very genuine question, given a projective variety, whether it has a rational curve or it has some other curve, some other projective curve or not. Okay, so let's not digress. So let's go to the other topic. It's already okay.